Hello everyone, thank you for watching this video. My name is Brent Griffin. This work is done in collaboration with Jason Corso, and today we're going to be talking about our work on Tukey-Inspired video object segmentation. The goal of this work is to automatically segment the primary object in video. This is done without any user-provided annotation or any dataset trained components such as an artificial neural network. Instead, we use low-level vision cues, such as visual saliency, which can be processed on individual frames, or optical flow, which evaluates the frame-to-frame changes in pixel intensity. The primary challenge in this work is determining which data sources are reliable for a given frame of video. Video characteristics can change dramatically from frame to frame, and the ability for a specific data source to identify foreground objects also varies. First, we look at the outlier thresholds for a given data source. This is calculated using the Tukey outlier constant in the interquartile range, which is the distance between the first and third quartiles of data. The outlier thresholds, denoted as O1 and O3, are essentially points far outside of the range of quartiles of data above and below the median. Next, we identify pixel-level image data existing outside of the outlier thresholds. Note that many instances of image data do not have outliers. Finally, we sum all of the data offset from the median existing outside of the outlier thresholds. The quantity of data outside versus inside of the thresholds determines how reliably we can identify a foreground object. Let's look at a few examples for optical flow. In the bus video, we have a bimodal distribution that reliably identifies the bus as an outlier. In the Mallard video, rippling water causes a much wider distribution of optical flow with no meaningful outliers. In our third example, the dancer is reliably identified in flow data when the camera is relatively stationary, but the same data source becomes unreliable once the camera starts moving. In all cases, the outlier scale helps us identify how reliably a data source can track a foreground object in the current frame of video. Using the outlier scale, we are able to adaptively evaluate and combine multiple data sources to identify the primary object in video. After using this initial estimate to identify foreground objects, we use supervoxels to refine object boundaries to improve segmentation performance. This is done by first generating supervoxels from the original input video. We evaluate our initial Tukey-inspired estimate of foregroundness within the boundary of each supervoxel, and then form a consensus to determine if each supervoxel belongs to the background or foreground. Finally, we use this consensus to refine our initial estimate and output our Tukey-inspired segmentation. One of the benefits of our segmentation approach is that it is generalizable to many types of video. Thanks to our outlier scaling, it is also robust to changing video characteristics. In the parkour video, we see a moving camera, a dynamic foreground object, and partial object occlusions. Next, let's look at a new paradigm for the problem of video object segmentation. Assume that we are given many estimates for the same foreground object. Using a variant of our initial outlier scale, we can also combine multiple binary masks together. First, we collect a set of binary masks for the same video frame. Next, we count the number of foreground pixels in each of the masks, and define a new outlier scale based on the foreground pixel quantities across the set. Finally, we combine the masks using their outlier scale estimated reliability, and repeat this process across the entire video. This process leads to a collectively more robust method of segmentation that we show in our paper to outperform all prior individual segmentation methods. For the last part of the video, we provide a quantitative and qualitative comparison to the current state of the art on Davis, starting with methods that are strictly unsupervised. In the top left and right, we have our Tukey-inspired segmentation method with and without supervoxel consensus refinement, which achieves state-of-the-art results. On the bottom left, we have NLC, which is the second best standalone method on Davis. Finally, on the bottom right, we have a Tukey-inspired combination of 8 unsupervised methods that outperforms all prior segmentation methods. We emphasize that this level of improvement was repeated when combining segmentations from all levels of supervision on Davis. For our last comparison, we look at our Tukey-inspired combination method on the bottom right against the 3 leading supervised segmentation methods. Thank you for watching our video. If you're interested in learning more, we recommend checking out our paper titled Tukey-Inspired Video Object Segmentation. And if you would like to try these methods out for yourself, please visit our GitHub page at the address shown here.